Hey everyone, today we're going to pull back the curtain on something really cool in digital logic. It's almost like a secret handshake, a trick that lets us do this amazing swap right at the core of how computers, well, think. We're diving into De Morgan's theorem. All right, let's just jump right in with a question that sounds like it should be impossible. Can you take a bunch of ands and just replace them with ors and still get the same result? I mean, that sounds crazy, right? It's like trying to swap plus signs for multiplication signs at a math equation and just hoping for the best. But here's the thing, you actually can. You just need to know this secret twist. Okay, but before we get to that big reveal, we've got to do a quick refresher on the main characters in this story. These are the fundamental logic gates, right? The basic building blocks for, well, pretty much everything digital. So first up, we've got the AND gate. Now this one's the strict one, It only gives you a true, a 1, if both of its inputs are also true. Input A and input B have to be 1. If even one of them is false, a 0, then the whole output is false. It's totally all or nothing. Then you have the OR gate, which is way more chill. This one's happy as long as any of its inputs are true. So if A is true, or if B is true, or even if both are true, you get a true output. It's the any will do kind of gate. And last but not least, we have the NOT gate. Some people call it the inverter. It might be the simplest, but wow, is it powerful? All it does is flip the input. That's it. You feed it a 1, it spits out a 0. You give it a 0, you get a 1. It's the opposite gate. And this little guy, this is the secret ingredient to our entire mystery. So, back to our magic trick. How do we actually swap ands for ors? Well, the answer comes from this brilliant mathematician from the 1800s, Augustus de Morgan. He figured out these two just beautiful twin theorems that are pretty much the foundation of simplifying digital logic. And here they are. Just look at that. They're perfectly symmetrical, like they're mirror images of each other. The first one says that if you not an and, that's the same thing as knotting each input separately and then oring them together. And the second theorem? It's the exact opposite. Knotting an or is the same as knotting the inputs first and then anding them. This is it. This is the secret. The swap totally works, as long as you flip everything along the way. All right, so that's the theory. Cool, right? But let's actually put this to work. Let's see how we can use these rules to take a messy logical expression and just clean it right up. So we're going to tackle this expression right here, a plus bc prime. Now, looking at it, it's kind of a mess. You've got an or, that's the plus sign, an and between b and c, and that little apostrophe on the outside means the entire thing is being knotted. So our job is to basically break up that big not bar and simplify what's inside. Let's walk through this. First things first, we're looking at a big OR operation, A ANDed with BC, and the whole thing is knotted. So we use Theorem 2. We can break that long not bar over the top as long as we flip the OR in the middle to an and knot each piece separately. That gives us A prime and the whole BC term, which is also prime. See what we did? Now we've got another not bar, but just over the BC. That's a knotted and, so we use Theorem 1. We break that bar, flip the and to an or, and knot the b and c. And boom, we get A prime and the quantity B prime or C prime. From there, you could distribute the terms if you wanted to, but the hard part, the De Morgan part, is done. We've completely broken down that nasty outer negation. Okay, so that was a fun little logic puzzle. But who cares? Why is this so important that it's considered a cornerstone of computer science? Well, it all comes down to two things, elegance and efficiency. Here's the deal. De Morgan's theorems give us this incredibly powerful tool. When engineers are designing the actual physical circuits inside our phones and computers, they can use these rules to simplify the logic. And simpler logic means you can build the circuit with fewer parts. And fewer parts means it's cheaper to make, it uses less battery power, and a lot of the time it's even faster. All of that just from knowing how to do this simple, elegant swap. And this really gets to the heart of it. This quote basically says it all, right? The theorems are the official rulebook for swapping ands and ors. You can do it as long as negation is involved. It's this beautiful, fundamental link between two operations that we normally think of as complete opposites. So that leaves us with something to think about. We just saw how these two core pillars of logic, and or, can basically be turned into each other. And it kind of makes you wonder, right? What other rules in technology, the things we just assume are fixed, are actually way more flexible than they look. What other secret swaps are out there, just waiting for us to find them? It's a pretty cool reminder that sometimes the most powerful way to handle complexity is to find the simple rule that lets you flip the whole problem on its head.